Hello students, welcome to the second lecture on canonical forms, and in this lecture we'll discuss the diagonalizable operator. Let T be a linear operator on a finite dimensional vector space V, then T is said to be diagonalizable if there exists a basis of V of which each vector is a characteristic vector of T. In fact, what is the meaning of this? Means simply you will be having a basis of V and corresponding to which if you obtain the matrix of T, that matrix should be a diagonal matrix. Let us see the explanation over here. Let B equal to V1, V2, Vn with the basis of V such that each Vi is a characteristic vector of T. Then by definition of characteristic vector, for each Vi there exists a characteristic value Ci such that you can write T of Vi equal to Ci Vi. Then Ci is the characteristic value. If you put here I equal to 1, 2, 3, n, T of V1 you can write like this, T of V2 like this, T of Vn like this. Now the matrix of T with respect to this ordered basis V1, V2, Vn can be written in this form. Then you can see those characteristic values C1, C2, Cn are at the diagonal of this matrix MT. So now this is a matrix of T and which is a diagonal matrix. So you can say the which is a diagonal matrix whose diagonal elements are the characteristic values of T. So I think the definition of the diagonalizable operator is clear. Now the remark: T is also said to be diagonalizable when characteristic vectors of T spans V. That means the characteristics vectors of T also generates V. Say V1, V2, Vn, etc. generates V. Now we see this example 3, and it is related to the already discussed example 1 in lecture 1, where T has no characteristic values. Therefore T is not diagonalizable, because in view of the above definition, if there is no characteristic value, then how we can talk about the diagonalizability of the operator T? So for that matter, in example 1 discussed in the last lecture, T has no characteristic value, therefore T is not diagonalizable. Now look at the another case. We call it example 4 and it is related to example 2. The characteristic polynomial of T was this fx equal to x minus 1 x minus 2 square. In this case you have the characteristic value, still it will not be diagonalizable. See the situation. Here we observe that there is a one-dimensional space of characteristic vector corresponding to characteristic value 1, and there is a one-dimensional space of characteristic vector corresponding to characteristic value 2. Therefore the space of characteristic vector corresponding to both characteristic value cannot form a basis of R3, because dimension of R3 is 3. In fact, the dimension of sum of the dimension of these two must have been 3. So that is why T described in example 2 is again not a diagonalizable operator. Now look at this definition. Another definition here. Let T be a diagonalizable linear operator. Let C1, C2, Ck be the distinct characteristic values of T. Then there is an ordered basis B in which T is represented by a diagonal matrix, which has Ci's on the diagonal, and each Ci is repeated certain number of times. And if each Ci is, again I repeat this line, if each Ci is repeated certain number of times, then diagonal matrix has a block form MT equal to C1 I1, C2 I2, Ck Ik. Here I1, I2, Ik are the identity matrices. If C1 is repeated 2 times, then I1 will be a 2 by 2 matrix. If C2 is repeated 3 times, then I2 will be a 3 by 3 matrix, and so on and so forth. In general, you can say that Ij is the dj by dj identity matrix, where j is the multiplicity of cj, that is the number of times cj is repeated. Now from this we can have certain remarks. From the above matrix, we observe two things. The characteristic polynomial of T is the product of possibly repeated linear factors. Suppose C1 is repeated D1 times, then x minus C1 D1. And if C2 is repeated D2 times, then x minus C2 D2, etc. X minus Ck dk. It will be the characteristic polynomial of T in that situation. Second thing, di is the number of times Ci is repeated as a root of fx is equal to the dimensions of the space of characteristic vectors associated with the characteristic value Ci, because corresponding to a characteristic value Ci there can be several characteristic vectors, and those characteristic vectors forms a space, and dimensions of that space is equal to the number of times this Ci is repeated. The nullity of diagonal matrix is equal to the number of zeros which it has on its main diagonal. Now we have one lemma. Suppose TV equal to CV. T is a linear operator. F is any polynomial, then f of TV equal to f of CV. Means if C is the characteristic value of T and V is the characteristic vector corresponding to this, and then f of T again a linear operator on V, then f of T will have characteristic value f of C. And we have already discussed the proof of this lemma in the class. And lemma 2, let T be a linear operator on a finite dimensional vector space V. C1, C2, Ck be distinct characteristic values of T, and let Wi be the space of characteristic vectors associated with the characteristic value Ci. If we have the sum of all these w1, w2, wk equal to w, then dimension of w equal to sum of these. Or if bi is the basis of wi, then b equal to b1, b2, bk is the basis of w. Now we have one theorem, and we are writing this theorem without proof. Let T be a linear operator on a finite dimensional vector space V. Let C1, C2, Ck be the distinct characteristic values of T, and let Wi be the null space of T minus Ci. Now the null space of this can be written in this way also. Wi equal to V, those elements of V such that their image under this comes out to be 0. That is why we say this is the null space of T minus Ci. Then the following conditions are equivalent. T is diagonalizable. The characteristic polynomial of T is this, where dimension of Wi equal to di. And third condition is dimension of sum of the dimension of these spaces equal to dimension of the space V. So application of this theorem we can show in this example. Let T be the linear operator on R3, which is represented in the matrix form by this corresponding to a standard basis. Now we have to examine whether this T is diagonalizable. If yes, find the diagonal matrix. We have the solution. You are given that T can be represented by this matrix in certain standard basis. To find the characteristic polynomial of T or A, we can apply the elementary row and column operations over here, and determinant of x minus, basically the characteristic polynomial is given by determinant of xi minus a, that is this. Now to simplify this, we apply row and column operations, and by applying certain row and column operations we get that characteristic polynomial comes out to be this. So we can say the characteristic polynomial of T is fx equal to x minus 2 square x minus 1. Next, we find the dimensions of the spaces of characteristic vectors associated with the two characteristic values. Two characteristic values are x equal to 1 and x equal to 2. 2 is repeated root here. So corresponding to this, we find a minus I and a minus 2i corresponding to this. These are the two matrices. From here, in fact, the dimension of null space or nullity of T minus I is the dimension of space of characteristic vectors corresponding to characteristic value 1. Similarly, nullity of T minus 2i or a minus 2i is the dimension of the space of characteristic vectors corresponding to characteristic value 2. Now clearly, if you find here determinant of a minus I, that comes out to be 0, and we have at least one non-zero minor of order 2. So you can say rank of a minus I is 2, dimension of a minus I is 3, and nullity of a minus I is 1. Further determinant of this is 0. So again we have no non-zero minor of a minus 2i, but we have non-zero elements in a minus 2i. So rank of a minus 2i is 1, nullity is 2. Thus dimension of w1, that is the space of characteristic vectors corresponding to characteristic value 1, is 1. And dimension of w2, the space of characteristic vectors corresponding to characteristic value 2, is 2, where w1 and w2 are spaces of characteristics as mentioned here, and dimension of w1 plus w2 equal to dimension of r3, that is 1 plus 2 equal to 3. Hence by theorem 1, T is a diagonalizable operator, hence it can be represented by a diagonal matrix. Now by definition of 1 at page 3, in the standard basis R3, T can be represented by a diagonal matrix as follows. Mt equal to C1i, C2i. Here C1 is repeated, C1 suppose 1 and C2 is 2. 2 is repeated 2 times and C1 is non-repeated. So I1 is a 1 by 1 matrix and I2 is a 2 by 2 identity matrix. So that way you can write 1, I1 is 1, 2 this, and these are the 0 matrices of the corresponding order here. So in this way this matrix takes this form. Now it is a diagonal matrix. Here the characteristic values are at the diagonal. So in view of this discussion you can solve this exercise, and moreover along with this exercise you can study these sections from the book that is we have already shared at your group. Thanks for this lecture, and thanks for your attention here.